Well, thank you very much for having the opportunity to present today. This is really wonderful. The whole idea of this talk is to extend a methodology that I developed while working with colleagues at Albany to use MOA to design and reduce code to general interfaces to parallel and distributed computing. So if you read this paper, you'll see that that design will allow you to create OpenMP code and MPI code, and I did all of that in Fortran. So this talk is about extending that to GPUs. I'm going to turn my video off just to make sure that there's no delay in my audio. Next slide. So what is MOA? MOA is a theory of arrays where everything can be written in terms of array shapes and indexing. That's all there is. Array shapes and indexing with an algebra built upon that. And combined with the lambda calculus gives us the property of the Church-Rosser property, which means we can prove the equivalence of programs. So we can use mathematics in a very powerful way. Next slide. The MOA syntax and algebra is highly influenced by APL. And I included Ken's algebra in my dissertation out of deep respect for Ken, because he deeply believed that APL was a notation for a tool of thought and a universal algebra. However, it wasn't Ken who even thought of using shapes to define the array calculus. It was Phil Abrams in his dissertation, An APL Machine. Now, the interesting thing is HP actually built that machine. It didn't work because all of the reductions that he proposed were done at runtime. Maybe HP wants to build an MOA machine. So what I did in my dissertation is I put closure on that algebra. Next slide. So to begin, this study is about looking at an algorithm. We took Van Loan's Cooley-Tukey fast Fourier transform, took it right out of his book, page 46. And again, we must start with mathematics. And we've heard from a number of scientists that say they are scientists, they use mathematics, they are not software engineers. So given a choice, I wonder if they would want to just specify everything in mathematics. Next slide. So any algorithm I could have chosen. I could have picked any FFT algorithm, and I'll tell you in a couple slides why I did not choose Knuth's algorithm. I chose Van Loan's because it uses arrays. It used the Kronecker product. It was 1D, could easily be extended to ND, and it was very popular. And Van Loan is very respected. I worked with him, and you know, who doesn't know of Golub and Van Loan? Next slide, please. So MOA is a systematic algebra defined to reduce the FFT algorithm to a denotational normal form. What does that mean? It means I use linear and multilinear transformations to take the high-level mathematical specification and reduce it to the least amount of computation needing. So all loop optimizations are done in the equivalent of an AST reduction system. It's done before compilation. And then after we get this semantic normal form, which means in terms of Cartesian coordinates, the least amount of computation, all loop optimizations, we do dimension lifting, which means we break up different sizes depending on the target architecture. So if it's numbers of processors, something that's 2D turns into 3D. If we're mapping it to GPUs, there's more dimensions there. So something that's 1D turns into 4D or 5D. So what then happens, we describe that partitioning. And then by knowing everything at the intentional level in terms of loop transformations, we can map those dimensions to the paradigms like OpenAcc. So I will say right now, I cannot do my research without all the work that's going on in OpenAcc and the support for that to guarantee that the intentional information is mapped to paradigms that do exactly what we want. So what does this do? It allows us to mathematically prove the efficiency and correctness of a given algorithm as measured in terms of a set of metrics. So after we lip those loops and we know the sizes and speeds of things, we can predict what's going to happen. So one person mentioned having an interactive environment. I also see that. In other words, magic just doesn't just happen. What happens is the user says, I want to use this machine. So there's tables that say sizes and speeds. And so things get instantiated to say, okay, I know I'm on a GPU. I know I'm on this GPU. So again, in terms of the paper that I wrote with Rosenkrantz and Hunt et al., we want to have minimization due to size reductions, and we want to have copies and sends that are completely transparent to the user, where they would not have to worry at all, am I doing a send to a GPU, to a CPU, to an FPGA? Don't care. That's all behind the scenes. All the user has to say is, this is my environment, and the tools behind the scenes would happen. Such an approach would allow the user to achieve high-level optimization similar to what compiler writers are doing today. And of course, we need those compiler writers, and we know many people love Halide and all of that, and I do too. And you know, that is really great until we have something like this, but this is not going to happen until the future. We start with algorithms, we build applications, we compare and contrast to what's out there so that we can have things that are, you know, as good as code written by gurus. Next slide, please. So here's the meat, starting with Van Loan's. Now, if you go back and you look at Van Loan's algorithm, he does the bit permutation first, and then he does the FFT. Well, you know, we discovered through our experience that it's best to do the bit reversal and FFT at the same time. So we formulated it in MOA. So I'll just explain to you what this expression on the right means. You start with the vector. Again, it's radix 2. I view it as a hypercube. I transpose the hypercube, and then I index it. And because psi reduction happens, I'm not going to transpose the array. I'm going to reverse the indices. So what you see in the implementation here is the implementation of reversing the indices. So I reverse the indices. You see the C shift down there. You see the shifting going on. But we're doing the shifting because we're doing when we turn the Cartesian coordinates to an offset based on gamma, we have to do plus and times. Well, of course, we don't want to do plus and times. We're going to do and or. And again, this is a proof in my dissertation. Next slide, please. Oh, I want to point out one thing before we go on to this slide. The main reason I did not use Knuth's algorithm is I could not find any math. If anyone knows the math, all I found was an implementation. I have no way of communicating with Knuth except through snail mail. And I think I can reverse engineer it, but it would take time because he's using shifts and I'm using shifts. So it's possible. If there's somebody out there, please help me do this because Knuth's algorithm is faster. Next slide, please. So we started with Cooley-Tukey. We created the operational normal form. It enables one to choose the block size that gives the best performance for an individual machine. The generic program explained in the paper with Rosenkrantz, Hunt et al. Describes a sequential, shared memory, a distributed memory model, completely general, completely formal, complete copy send interfaces, transparent and different, general. And we started with this and proceeded our designs to do the exact same thing for GPUs. Okay, well, take it.
So I'm William Phan. I'm currently a scientific computing software engineer at Berkeley Lab. This is the result of collaboration I've been doing with Lenore for the past couple months. What we've been doing is taking the base CPU-only version from the Rosenkrantz et al. Paper, which is, there are 3 different versions of the Fortran code: the sequential version, the OpenMP version for multi-threaded processors on the CPU, and the distributed version with MPI for multiple nodes. In the beginning, we picked the OpenMP version, the shared memory model, because GPU, it has a unique memory hierarchy. I can argue that it's a mix between shared memory and distributed memory. Distributed memory in the sense that the device memory, the memory of the GPU, is distinct from the CPU, from the host memory. Unless you are using unified memory, in this case, we chose not to use unified memory because we want to isolate the time needed to transfer data from and to the GPU. However, within the GPU itself, the device memory or the global memory is shared between the different execution units. For NVIDIA GPU, it's shared between the symmetric multiprocessors. For AMD GPUs, it's the compute units, etc. There is also what is called the CUDA shared memory for the NVIDIA GPU, where you can share data between different threads in the same block. So this is CUDA terminology, a block of threads. This is what motivates us to use the shared memory version, which is the OpenMP version. And we, in the process of porting it, we just replace the OpenMP directives with OpenACC directives for GPU usage. Why did we pick OpenACC over other programming models like CUDA Fortran or HIP or SYCL? First one, and the most important one, is the ease of use of OpenACC, just like its motto: more science, less programming. You just sprinkle the OpenACC directives at the right places and your code runs on the GPU, which is awesome. The second one is you can maintain a single source code because the OpenACC directive is a pragma on C and C++ and Sentinel, specially formatted comment exclamation mark $ACC. So you just need to toggle the color flag to enable OpenACC. Otherwise, they will be treated as comments. So we are able to maintain a single source code for both the CPU-only version and the GPU-enabled version. The third one is OpenACC is portable, unlike CUDA or HIP or SYCL. So the same code, we test this on NERSC with the development resource Cori GPU, the GPU partition of the Cori supercomputer, which is a dedicated development resource for people wanting to, as a stepping stone to the new Perlmutter supercomputer at NERSC. But I also tested the same code to run on my own AMD GPU on my workstation with Fortran, and it works. And there are some rumors that Intel support are coming to with HIP, SYCL, and things like that. But that's just for the future when we say we get access to the Aurora supercomputer at Argonne, for instance, if we want to run there, which uses Intel GPUs. So in short, OpenACC is easy to use. We can maintain a single source code, and it's portable. And we have a list of several favorite features in OpenACC. The first one is full Fortran support in OpenACC, unlike, say, HIP, which is C and C++ only, or DPC++, which is also C or C++ only. The next one we like most is GPU. I think for AMD GPU, the term is wavefront, but yeah, it's the same concept. OpenACC provides 3 different levels of parallelism: gangs, workers, and vector parallelism. When you use the NVIDIA HPC SDK and you turn off the compiler flag -big M and then info equals Excel, you get this kinds of output that tells you which one is matched to which parallelism level is mapped to which hardware. So the gang is mapped to the block. The worker and the vectors are mapped to the threads. So this is wonderful. And we are planning an experiment because the point of MOA is the ability to mechanize everything to predict performance. So we are planning an experiment to vary the gang size, vary the worker size, vary the vector size, and find the optimal one, say for the V100 NVIDIA GPU on Cori GPU, or for the A100 GPU, or for the MI100 GPU on, say, we get access to Frontier on at Oak Ridge once it gets online. So we want to be able to do this kinds of experiments to get that table of performance numbers. We are proud to tell that we achieve competitive performance for the total runtime of the FFT with respect to QFT, the CUDA library that CUDA provides for FFT. And the timing is performed, it is in 5 parts: the initialization of the data on CPU, and then sending it to the device, and then the planning phase or the bit reversal phase, depending on QFT or MOA FFT version, and then the actual time needed to perform the forward transform of the fast Fourier transform, and finally the time needed to move the data back to the CPU. If you want to argue that if we just look at the FFT forward time, QFT is clearly a lot faster. But if we add up the planning time and the forward time and compare it to the bit reversal time and the forward time for MOA, we see that it is almost, well, it is competitive. And when you add the host to device and device to host, the graph looks like that. So the horizontal scale is the problem size in powers of 2. So we went as high as 2 to the power of 27, which is, with double complex type, is about 8 gigs of video RAM, I believe. Finally, another one that we love is the cache directive for using CUDA shared memory on NVIDIA GPUs. So in this case, we want the weights for the butterfly computation of the FFT to live on shared memory, so its accesses to the shared memory are faster. And we want also the little chunk that the data that is operated on the Z block for the current block, that also lives on shared memory for performance reasons. And we can just do $ACC cache, and as long as the sizes of the weight and the block fits in the maximum shared memory per multiprocessor, which I believe is 96 kilobytes for the V100 GPU, that's it. We automatically use shared memory. The next one would be a wish list of what we wish worked in OpenACC. The first one is we can't seem to get array reduction to work yet. This is introduced in OpenACC 2.7, but we still can't get it to work. The only way to get this work is by making a scalar variable, say temporary, and then this red part is temporary equals temporary plus math, and then after the reduction is done, vec of I equals to temporary. So that's not a true array reduction, in my opinion. So if anybody is can show how this works and with which compiler, we will be happy to see this go through. The next feature that we wish in OpenACC is manual synchronization routines. The left part is the CUDA equivalence for the device, for the whole GPU, for the stream, for the threads, and for the, which is the smallest unit of data you operate on as a group of threads. As far as I know, the only synchronization routine that's provided with OpenACC is ACC wait, which is equivalent to the stream synchronize. And there is no equivalent yet for the thread synchronization and warp synchronization. So we wish that would be made available in the next OpenACC version. The next one is something that we discovered. So in earlier NVIDIA HPC SDK versions, the initialization of the OpenACC runtime library happens at program start. And in the more recent version, I forgot if it is 21.5 or 21.7, the cost of OpenACC runtime library initialization gets into the first OpenACC call. So the library is initialized when the first call to OpenACC is performed. In our case, that was the host to device memory transfer. So we had to isolate that and put it outside of our timing. This is about 300 milliseconds, so it is quite a big chunk of initialization. We do the same thing with the CUDA FFT, with the QFT version, where the same thing happens. The first initialization happens at the very first call to QFT. So we created a fake plan, and then we destroyed the plan, and that takes about 200 milliseconds, and we don't time that part. Finally, it would be really great if OpenACC supports pinned memory. This is the equivalent CUDA Fortran syntax. Pinned memory is nice because it is always at the same place in CPU, in host memory, and it is faster to transfer data from pinned memory to GPU for NVIDIA GPUs. I believe AMD GPUs have a similar concept as well. So it would be nice if OpenACC has that. And once we are keeping an eye on OpenMP target offload, and once compiler support matures, like in Clang or in GCC or in NVIDIA HPC SDK, once the compiler support matures, we will port from OpenACC to OpenMP, because that will allow us to do the same programming model, OpenMP, for both multi-core CPU for multi-threaded parallelism and using the OpenMP target offload for the GPUs. Of course, we keep an eye on the CLAC and FLAC projects also, which Dr. Joel Denny yesterday gave a presentation on. So we also keep an eye on that, especially FLAC. We are waiting to be maybe the first of several users, maybe, if possible, of FLAC. We don't have any conclusions yet because this is still a work in progress, but we acknowledge that this research is supported by the DOE under the SBIR grant, and we are thankful for NERSC resources, especially Core GPU. We are also thankful for the NERSC support people. They are really helpful with all our tickets and all the trainings that they give. And we want to thank Max Katz from NVIDIA and Rishi Khan from Extreme Scale Solutions in particular, because we filed several compiler bugs with Max, and then Rishi pointed out several of our shortcomings in the code and things like that for optimizations. We also want to thank members of the Slack channel, MOA, Global Team, and OpenACC Hackathons. We've gleaned so many interesting and useful wisdom and insight from them. We also would like to thank the Fortran community for supporting us.